Hello everyone, welcome to KTU Classes. In this video, we will discuss a problem about substitute frame method whose theory we have discussed in the previous lecture video. The previous lecture video, if you haven't watched that yet, I will give the link in the description box below. So in this problem, they have asked us to analyze a frame for midspan positive moment on BC, and they have given that the total dead load is 12 kN per meter and total live load is 20 kN per meter. So the column heights are 4 meter and beam length is 6 meter. And this is our span BC, for which we will have to find the maximum midspan positive moment. So our ILD will be like this: a sagging moment in BC and a hogging moment on AB and CD respectively. So this is our substitute frame, which is loaded with dead load of 12 kN throughout the frame and a live load of 20 kN only in the span BC. Because in order to get a maximum positive sagging moment or positive moment in BC, we will have to load the live load on the span BC. The next step is to find the fixed end moments. We know the fixed end moment equation. It is given in the previous video. So if anyone hasn't watched that yet, please do watch that video. So fixed end moment of FEM AB is WL square by 12, which is 12 into 6 square divided by 12. And FEM BA is 36 kN. Similarly, WL square by 12. Similarly, FEM BC is equal to 12 plus 20 is 32 minus 32 into 6 square divided by 12, and FEM CB equals to 32 into 6 square divided by 12. And then the next step is to find the distribution factor. In order to find the distribution factor, first we'll have to find the stiffness coefficient for each member. So consider this member AB. What will be the stiffness coefficient? The equation for stiffness coefficient K is equals 4EI by L. So the stiffness coefficient for AB will be 4EI by L is 6 meter. Similarly, the stiffness coefficient for BC would be 4EI by 6 itself, and also for CD it will be 4EI by 6 since all the lengths are the same. And similarly, this, let's name this column I, J, K, L, M, N, O and P. Therefore, what will be the stiffness coefficient for the column IA? The column height is given as 4 meter. Therefore, the stiffness coefficient for the column IA would be 4EI by 4. Similarly, for AJ it will be 4EI by 4 and all others, since every column has 4 meter height. So, thus we consider a joint and each members and we calculate the stiffness coefficient. And the next step is to add all these stiffness coefficient at a particular joint. If we consider the joint A, we have member IA, AJ and AB. We'll add the stiffness coefficient of IA, AJ and AB, and we'll get 8EI by 3. And similarly, you'll have to compute the sum of stiffness coefficient for each joint B, C and D. Then we'll find distribution factor. Distribution factor, the equation for distribution factor is K by sigma K. K is the stiffness coefficient of the member and sigma K is the stiffness coefficient, sum of stiffness coefficient at that joint. So if we consider A1 or AI, we have named it as I. We will have 4EI by 4, which is equal to EI divided by 8EI by 3, which is equal to 3EI by 8. And for AB, it is 4EI by 6 divided by 8EI by 3, which is 1 by 4. And similarly, we'll have to calculate the stiffness distribution factor for all the other members. And the next step is drawing the moment distribution table. We all know moment distribution table from the previous semester. If not, you'll have to refer back to your notes and learn moment distribution table. In this substitute method, we'll have to perform 2 cycles of moment distribution procedure. So considering joint A, B, C, D and the members in that joint A, B, B, A, B, C, C, B, C, D and D, C. Only we consider only the B because we need the maximum span moment at B, C. And then we'll write the distribution factor corresponding to these spans. And then their fixed end moment is also written. And then we'll start balancing. When considering joint A, there is only a member called AB and the fixed end moment is minus 36 kilonewton meter. So what we'll have to do is, we'll have to multiply this minus 36 we'll have to take minus of minus 36 and multiply it with 0.25, which is minus of minus 36 is 36 and multiplied with 0.25 we will get 9. And similarly considering joint B. In joint B we have 2 fixed end moments, that is 36 and minus 96. First we will have to take the algebraic sum of these and then again similarly minus that algebraic sum. For example 36 minus 96 we will get minus 60. We will have to convert it as positive, that is plus 60 into the distribution factor of the corresponding member into 0.2, which will get 12. And similarly for CD also we'll have to compute the algebraic sum and then compute the balancing moment, and also for DC. Then we'll do the carryover factor. What we do is carryover factor is that we'll take 9 by 2 here, 9 by 2 which is equal to 4.5, and here 12 by 6 which is equal to 12 by 2 which is equal to 6. And similarly here 12 by 2, 6, and here minus 12 by 2 is minus 6. Here minus 12 by 2 is minus 6, and here minus 9 by 2 is minus 4.5. And then again we'll do another balancing cycle and also a carryover moment cycle. And then we'll add these moments to get the final moment, that is starting from FPM minus 36 plus 9 plus 6 minus 1.5 plus 0.15 we will get minus 22.35 kilonewton meter. And similarly for BC, for BA, BC, CB, CD etc. we will get this moment on adding these from FPM onwards. And the span we require is span BC or CD. So we will so what we need is the fixed end moment at B and the fixed end moment at C. The final moment at B and final moment at C, which is minus 89.85 and 89.85 kilonewton meter respectively. And then we'll draw that span, mark their final moments, and we'll have, what's our question? Our question is to find the maximum or midspan positive moment on BC. So here we'll consider a section XX correct at the midspan and we'll find the moment about this section XX, as we have learned with MOS, mechanics of solids, in our 3rd semester, I think. And the maximum midspan moment ME, consider this joint as E. ME equal to minus 89.85. That is, looking to this side, considering the left hand side, we have an anti-clockwise moment of minus 89.85 and we have another anti-clockwise moment which will be given by the UDL, which is minus 32 into 3 square divided by 2. 32 is the load, and we have our entire span is 6 meter. And half of that span is 3 meter, therefore 32 into 3, which is the total load. It will be acting at the center of at a distance of 3 by 2 from X, that is minus 30, and it will produce a hogging moment. That is why minus 32 into 3 square or else minus 32 into 3 into 3 by 2, which is minus 32 into 3 square by 2, plus 32 into 6 by 2 is the reaction at B, because our total load is 32 into 6 acting at the center, and the reactions will be 32 into 6 divided by 2, and that reaction will act at a distance of 3 meters from X. Thus we get our midspan positive moment on BC. And then we'll have to draw the bending moment diagram. So this is our first problem. This is a pretty simple problem. In substitute method, all we have to know is the loading condition, and then we'll find the fixed end moment, and then we'll find the moment distribution table, and then we'll find final moment, and then just find the midspan positive moment if that is what they asked. So thank you. Please feel free to like, subscribe and share. We'll be coming up with more videos. Thank you.